It's good to have you all with us. The main topic of this webinar is remote regions. I think in almost all of the technical presentations, the word remote appears in the title. So there will be a clear red thread throughout this 1.5 hour that we will spend. A point of order is that we will record this webinar. So just be aware of that. If you don't want to show your camera, or you should be aware of that. And after this has finished, we will also eventually publish the recordings of the individual talks and possibly also the slides. And we'll get back about that later on after this webinar. So the organization of this is, I will scroll, I hope you will all see my screen. The agenda is, we have starting off with two more general presentations about the two projects, starting with the Ensure project and then the Arctic 6G project. And then we have another three technical presentations of work in these projects. So I won't talk any further than that. Let's move on. Let's welcome the first speaker, and that is Nurul Huda Mahmood from the Ensure project. So I will stop sharing my agenda now, and that will hopefully allow you, Nurul, to join in. So the floor is yours.
Okay. Thank you very much. So I should just say, yeah. Good. Let me just share the slides. Okay, so hello and good morning, everyone. So welcome to this webinar, also on behalf of the Ensure 6G project and also on behalf of myself. My name is Nurul Mahmood. I'm from the CWC, Center for Wireless Communications at the University of Oulu, and I'm the PI for this Ensure 6G project. So maybe a little bit about the Ensure 6G project, just for those of you who are not aware of the project. As Jaap mentioned, we already had a similar webinar last time, but many of you are aware, but just to make sure that we are all on the same page. So this project is a 3-year project that started in September 2023. So we are almost in the middle of this project now. And it has two main partners, the University of Oulu from Finland and Mid Sweden University from Sweden. And a PI from Mid Sweden University, Aamir Mahmood, is also here online, and he will have a presentation later today. We also have two associate partners, so they are not getting any funding from the project, but then they are still contributing in kind by providing their expertise. From Finland, we have Soli, so there's a typo here, it's Solita. Solita, that's an IoT company. And then we also have Starbit, which are making IoT devices in Sweden. And then we have some sort of advisors, Viola. That's the Finnish operator of the rail network in Finland, and Drone Innovation from Sweden. So that's the project consortium. So what's this project about? Jaap, as you mentioned, the remote connectivity or rural connectivity is the red line that's connecting these two projects, and also that's the thread that's somehow connecting the different work packages within our project. So basically, the project goal is to look into efficient connectivity solutions. We have two goals. So the first goal is to look into efficient connectivity solutions, and the second goal is to look into remote sensing techniques, mainly for remote monitoring of the logistic infrastructure in remote areas. So as you can see here, you have different pictures of logistics infrastructure. So we have the, let's say, trucks and so on. but we also have the rail network. So these are different examples of the logistics infrastructure that we are targeting as use cases. And then we are basically trying to see first, how can we provide efficient connectivity solution, wireless connectivity solutions for these use cases? And second, how can we use remote sensing techniques to improve the, let's say, remote operation of these use cases? So that's basically the main goal of this project. And of course, the objective is to have this kind of maintenance, reduce accidents, improve efficiency, and so on. So in terms of the project goals or outcomes, so we have short-term and long-term goals. Short-term goal is, of course, to, first of all, make sure that this project completes successfully with, with some good results, and also probably to spin off into new proposals and new research ideas that we can continue further with the collaboration, and then disseminating this the outcome of this project, for example, through this webinar and also other similar events. Okay. And then in terms of the long-term goal so we have two. First is the let's say flagship status in supply chain digitalization and automation. So basically to really look into how do you say effective solutions or long-term solutions for this infrastructure problem, because you know that in remote areas this is the main problem, that we have this logistics use cases and we need to provide efficient solutions for those, right? And then the second one is not the technical, but it's more on the, let's say, impact of this project is to create this North Nordic ICT belt and to attract more talents to this region, because you know that this is also one of the challenges that are being faced in these remote areas, basically attracting and also retaining talents to ensure the development of this region. So the title of this talk talks about resilient network. So I just added this slide to tell you about what do we mean by resilient network. And this is a topic that we are discussing a lot within 6G Flagship and within CWC, especially because we believe that resilience would be one of the main keywords of 6G and beyond 6G networks. Okay. So, of course, there are also other similar terms, for example, reliability, robustness, dependability, and so on. So how does resilience differ or resilient differ from these other terms? So one thing, for example, the closest, let's say, existing solution that you can find to resilience is URLLC as defined in 5G. And that's basically telling you that, okay, we need to guarantee certain reliability and certain latency guarantees for communication, right? But URLLC as defined in 5G has some limitations. So first of all, it's not application aware. And as we all know that different applications have different requirements. So you cannot just say that, okay, I need reliability 10 to the power of -5. And it's not like one size fits all, right? You may have industrial applications that requires 10 to the power of -5 reliability, but you may also have other applications that may require, let's say, 10 to the power of -2 reliability, right? So that's one thing. The other thing is that URLLC focuses mainly on reliability and latency, as the name suggests, as the KPIs. But when you talk about resilience, there are also other KPIs. So one example can be that if, suppose the network fails for some reason, right? How long does it take for the network to come back to its normal state, right? So time to recover. And that's an important metric that's not covered in current URLLC in 5G. Then also the other thing is the scalability, because URLLC as defined by 3GPP is for the link. It's defined for layer 2 link. But then we all know that wireless networks is not limited to a single link, right? Wireless is a multi-hop network. So how do you scale URLLC to the whole network, right? And of course, when you talk about resilience, you cannot avoid the term security, because security is an important pillar of resilience. So basically, if you want to talk about resilience, we believe that to make a network resilient, it should be application aware. So you need to provide different quality of service guarantees for different applications, and you need to be able to differentiate between different applications. Secondly, of course, we need to also expand the horizon and going beyond reliability and latency to talk about other KPIs. Thirdly, scalability is very important because wireless networks, as you know, is not just limited to a single hub or even to a, let's say, local area network. So when you scale things, then of course you have different problems that need to be solved. And finally, security should be built in by design to make networks resilient. So this is addressing the first part of the title of this talk. So resilient networks. Secondly, then let me also give you some updates of what we have been doing in this project. Of course, so one aspect of this resilience is the connectivity solution, right? And as I said, in this project, we are looking into two different problems. So one is the efficient connectivity solution, and then the other is remote sensing. So in terms of the connectivity solution, as you can see from this figure, which also will be expanded further by my colleague Jian in his talk later. So Starlink, you can see it has very good coverage in mainland Europe, but when you look at the remote region in Finland, let me just use the laser pointer here. Yeah, so you can see that it's not very well covered. And this is that, as Jaap, you mentioned, this is the main challenge of remote regions, right? Existing solutions are not sufficient for these remote regions. So we were thinking that can we have, of course, another option would be to have UAVs hovering above, but then you know that UAVs, since they're like at 50, 100, 200 meters, so their coverage region is very limited. So an intermediate solution that is between UAVs and satellites is HAPS, high altitude platform systems. So basically, these are flying devices that can be static. They're around 10 to 20 kilometers above the ground, so they're above the stratosphere, so you do not get many of these atmospheric challenges. But then they can be a solution to provide connectivity covering a wide region, right? So this is one thing that we are investigating in this project. And I have here, of course, one result that just shows that in our, let's say, preliminary study, we have tried to evaluate what would be the performance of a HAPS-mounted LoRa network. So you have here HAPS height. So when HAPS is at different heights, and you have here the distance from the origin to the network to the border. So basically the radius of the coverage region. And what is the success probability of connections or coverage probability of connections with different LoRa spreading factors. And you can see here that, for example, with SF12 or with LR-FHSS, we can get quite good coverage probability, even with large covering a large area with a large radius, right? So this is, of course, some initial results that we have been investigating. And as I said, my colleague Jian will provide you further details, so I will not dwell on this any further. Then the other part of our project is to look into this data fusion techniques, or let's say remote sensing techniques. So the main thing is that how can we use sensor data? So maybe I will go to the next slide first and then come back to this one. So how can we use sensor data, different data from different sources? So you can see multimodal data. So not only sensor data from the, let's say, logistics operation, but also data from other sources. And how can we use this to do predictive maintenance so that we can have much more efficient logistics solutions, right? So one thing that we are investigating now, as you can see here, is the use case of the rail network. So basically, to look into the impact of the weather on the delays in rail traffic in Finland. So we have collected data from the Finnish rail operator of the delays across a large number of periods, so across multiple years, the delays in each station. And also together we have collected the weather data from the Finnish Meteorological Institute. And now we are trying to collate this information and trying to find the correlation between the weather and the delay. And then first step is to find the correlation, and the second step would be to come up with a predictive model, so that by just looking at the weather forecast, we can try to predict what would be the delay at a given station. Of course, it's not as easy as it sounds, because you have different artifacts at different regions. So for example, in the north, snow is one of the main contributing factor. In the coastal area, then the wind speed is a big factor. And then in the south, you have other parameters that impact this delay. So this is a work that is ongoing, and hopefully we'll soon be able to publish our initial results in some conferences. So these are the, let's say, two arms of this project that we are looking into. And then I will go back to this slide here. So semantic communication is also that's one part of this, where we are trying to answer the question like how can we make the transmission of this information more efficient. So in this case, you have this remote operator that is doing this remote operation of timber, these trucks that are carrying timber. And of course, as you can see here, you need to send a lot of images here. And that, of course, imposes that's a bottleneck on the connectivity, because you need a lot of big data pipe to send these images, right? So we were asking the question, can we use semantic communication to make this much more efficient? Because when you have a lot of images, but then we do not need to send all those images. So if we can find a way to extract the useful information from this image, and then only send that information, then of course the connectivity becomes more efficient, because you need a smaller pipe to achieve the same thing. So that's also another thing that we are looking into, and probably my colleague Aamir will detail this a bit further. So, okay, so, and then the last thing that I would just say here very briefly is that there's also this problem of sun curve monitoring, and we are trying to build some devices, some sensor devices that can try to sense the rail tracks, so that we can predict the sun curves, because you know that this is a big problem, especially in the summer, because although we are in a cold region, but then the summer can be very hot, and then you get this problem, because these sun curves do not only depend on the temperature, but it also depends on how fast the temperature is changing, and this happens often in this region. So we are looking into building sensors to try to address this problem as well. Yes, so with that, that's the last slide here. So I just, to summarize, I just gave you a very quick glimpse of the different aspects that we are researching in this project. And we are 1.5 years into the project, so we have made some progress, but hopefully the next 1.5 years will be reaping the benefits of this progress and coming up with all the publications and the results. Yes. With that, thank you very much for your attention.
Good. Thank you, Nurul. So there is room for some questions, if there are any. I have 1 or 2 questions. So I was wondering on these new KPIs. On one of your first slides, you mentioned the new KPIs, and you mentioned up the time it takes to recover for a network and so on. Is coverage by itself? Do you consider that a KPI? The mere you go later on into the details of rural remote coverage. Is that?
Yeah, I think that's a very, very good question, and that's of course something that we are looking into. So,
and also probably sorry for interrupting, but also it is related to the service. There's not one kind of coverage, perhaps.
So that's actually connects to this application awareness. That what is the service availability, and that's more that's maybe the more accurate term. So when is the service available in this region, right? And that's of course an important KPI that has been overlooked, but that we believe it's important for resilient network, because in remote areas, then coverage or service availability is an important metric to consider.
Yes.
Then you basically have to be aware of connectivity of various different communication methods and link that to these services.
Yeah.
Yeah, good. Perhaps one other question. I was thinking of this. If Starlink, and you showed the map of the coverage map of Starlink, for instance, right? If that is meant for remote areas, so how come? Do we understand why the deployment is as it is? Why do they deploy so much fewer satellites in the polar region? Do we understand the business ideas? And is this a threat, or is this a concern, right? Because we hear that Starlink and satellite communications are going to solve our coverage problems, right? Well, will it? Will it solve it?
Yeah, I don't know, but I think that this is the scarcity of the people and how much you can earn money from these people probably in the area where it's very scarce, there is living only 7 to 10 million people. And in Central Europe, it's in one city, 7 million people.
Yeah.
But they are not using Starlink, so.
No, so I think it seems to me a point of concern that the promise that we are giving people for that's LEO satellites are going to solve everything for everyone. Well, it may not be the case, right? If operators eventually tend to deploy the satellites constellations in a certain ways.
Even this scarce number of satellites is currently enough, but if there will be more users and per beam, then not anymore. Yes.
Okay. Thanks again, Nurul, for this first presentation.
Thank you.
So let's move on in the agenda. The second talk will be from the Arctic 6G project, and so that talk will be given by Mikael Nilsson. So I hand over to Mikael now.
So, can you hear me?
Yes, we can.
Yes.
Perfect. Yep, checking. So my name is Mikael Nilsson. I have the honor to be the coordinator and project manager for this project called Arctic 6G. So I will tell you a little bit what we have been doing and will be doing the rest of the time in the project. Oops. But I will start with giving you some background. Some years ago, we started with another project called Arctic 5G, actually. And that was about both, the team was more or less looking the same, but this was also to get better links between Oulu and Luleå in this region. So we had a kickoff in Luleå at that time, and what was kind of special with this project was that most of the time we had the pandemic situation. We couldn't meet physically, but this was one of the rare pictures from where we actually could meet. Most of the work was done remotely then. So that ended in September 22. And we were focusing on bringing industries together, actually, and offering test opportunities. And I would say one result later on that showed the usefulness of this project was that we are now both Oulu University and Luleå University involved in a flagship project, Horizon project, about autonomous robots. And we use one of our kind of test environments, which is very similar to a mine, but it's another inside the mountain, but it's not a real mine. So we could test robotics and drones, etc. So this was just an example of the importance of this kind of project, where we can bring our labs together and create links with industry. But now to what I'm actually here to talk about, the Arctic 6G scenario. And it has a little bit been mentioned already. This was or is focused on robustness and security of tomorrow's 6G networks, etc. So rural regions, we have a special case there. We heard a little bit about it already, but this has been a struggle for decades, long time. And this is also need of continue to develop the secure and reliable connectivity services for all in this kind of regions. And I mean, this is also about connectivity and the internet services in these rural areas, and our region must improve, actually. It's an important region for many reasons. There is a huge asset of natural resources, etc., etc. So industry needs, and people who live there needs this connectivity, even in the 6G era that is coming up. So this project will help then the future 6G network to improve the societal resilience in this rural Aurora region. That's why we are running this Interreg Aurora project. And the objectives within this project is to develop new technologies for 6G cellular networks, available then for uptake in this of the new 6G standard during this year. That is one of the indicators in this project, the uptake by companies in industry. And it's also about exploit and combine the expertise in cellular networks with Luleå and Oulu universities. This is an area that is constantly growing. As I see the collaboration opportunity with Finland and Sweden always increasing. And thirdly, involve industrial networks in Sweden and Finland. We have big telecom players, for example, on both sides. Just to mention Ericsson and Nokia, known examples, and the SMEs around these companies and in these areas. So the goals with the project, we are now in our final year, I would say. So the goal with this project is look into energy efficiency of 6G technologies for these rural and remote areas. Also look into the tools to evaluate and measure cellular coverage inequality. Network security functions, of course. Security is always an issue here. IoT device localization methods. And finally, an understanding of connectivity needs. That is maybe not known for all, but this is also one of our goals, to put a finger on these needs and the importance for developing the regions. So how do we do this? Of course, we have traditionally structured the project in work packages and activities, but the three last ones are the most important. Key wireless technologies in rural areas. And there you have three tasks: IoT device localization, tracking, authentication. We have also been working with the low power 6G local access solutions. And thirdly, cybersecurity in 6G networks. This is the third work package. The fourth one is looking at the social needs and innovation, the people who live here. So internet availability and coverage, KPIs for that. And in our region, we have a huge popularity of Sápmi people. And so Sápmi connectivity needs, we have been looking at as a special case. The reindeer herders in very, very rural areas is just one group of people that have their needs. And the last work package, demonstrations and measurements. And here we look into the implementation demonstration of what we're doing. And the last task there, windmills and cellular towers. This is something that my colleague Harri will talk about a little bit later, dive into that a little bit more, how it looks like. So some results that is available for the moment. If you go to the webpage of our project, we have listed some of the publications coming out from this project. This is just one kind of results. But we will at the end of the project, of course, address the indicators that we have received from the Interreg office, which is very much about uptake and use of results for others, like industry and SME companies. So you will find more there if you go to this webpage. So the team in this project is myself, then Jaap, who is moderating, Harri sitting just across the table here, and Eila just sitting next to me. We are all here together with some other colleagues. Carl Andersson up upper left, he is starting up a new subject, so he's not on the team anymore. But this is basically the teams and many other colleagues doing this kind of work. So by that, thank you for having me here as a presenter of this project.
Excellent. Thank you, Mikael. Any questions for Mikael? Also from the audience or from people here?
I may have a question, but I don't know if it's better for now or with Harri.
Go ahead.
Do you have any kind of way to measure what is like how many of the Sami people are like without connectivity or without their needs? Like is there an official number?
Maybe Harri knows that better. We've done a lot of this work.
There is no really numbers there, and because often they live in the villages that have connectivity, bad or good, but they have connectivity. But when they go to do their business, reindeer herding, then they often don't have connectivity, and it's security problem and other things related to that.
So the problem is more like it's not exactly where they live, but where they have the business area.
Yeah, it's also where they live. As you know, even in big cities, we have problems if you are not living in the city centers or areas where they have built build connectivity, but outside of those, you have always problems. At least if it's cellular coverage. Yeah. So, but most biggest problems are in the wilderness. Yeah. And they do their work in wilderness.
Yes.
Yeah, perhaps I can add to that as well. So there are the national regulator in Sweden, for instance, they do follow up on internet connectivity on a yearly basis. That's basically the task of the regulator, one of the tasks of the regulator, right? But they measure connectivity mostly in terms of percentage of the whole Swedish population, right? So you would get numbers like 98% of the Swedish population is covered or is connected, right? And the interesting thing is then those 2% who are not, where do they live? And the statistics do not like give conclusive answers to that question. So it's also we should push perhaps the regulators to give them means to measure also that kind of inequalities, if you will. Okay, let's move on. We have the third speaker coming in, and that is Harri Saarnisaari from Oulu University. He's going to talk about wind turbine towers as cellular infrastructure. Harri, go ahead.
Okay, good morning, everybody. I will talk about how we can possibly use windmill towers as cellular towers. We have studied this problem since the beginning of the project. In the first year, we did the initial studies, and then it was halted, and now we have continued working on this problem. And in general, if you look at the literature and internet, you can see that there are some studies, but not giving all the answers what you need. And that's why we are still continuing this process. So for example, military guys in Finland, Sweden, and elsewhere, they are saying that these windmill towers are disturbing their radars, and radars are RF things. So in the civilian cellular connectivity, we would expect similar kind of behavior for our signals, but there is no data available how bad is this disturbance. Is it really matter in wireless communication? So that is open question. I have seen some studies, but they are so theoretical that you cannot understand what is the attenuation of these blades. Or they have not concentrated on those, but other aspects on the propagation. We already know that some windmill farms are using these 4G networks or maybe now 5G networks, but they are in the sea. The reason is that in the sea level, there is this figure, you can see this base. So in the sea, these towers are put above the base, and they can put these cellular antennas on the top of this base. So there is platform, these cellular devices below the blades, but still well above the sea level. So it's not problem there. But at the land, if you look at this land windmills, there is not this kind of base. So the problem is where you can put these antennas. So then this slide is about what are the potential benefits, why we should do this kind of things. So we have discussed with the windmill farm owners or operators, and they said because these windmill farms are often in remote areas and people have to go there for work and other things. And if they don't have connectivity, and it's wireless connectivity, when they are moving there, they have problems, and it is inefficient because they have to drive to places where they have connectivity, then drive back to place where they are doing things, and so on. They also need local connectivity around these windmill farms. So it's needed for the people who are doing business there. Then it would be nice to connect these towers to collect data, doing joint control and so on. Then then they have, I think mostly they have fiber coming there, but if that fiber breaks, then there's no connectivity at all. So this wireless connectivity could be a backup solution, while it provides this local connectivity for moving people. Then if people would know that they are using these windmill towers as cellular towers in remote areas, maybe they would be more acceptable towards these towers. And then I'm not sure what is how big volume is this business case, but there is at least minor possibility for doing business. Those were the benefits for windmill operators. Then for mobile operators, if they could use these towers, is that there's reduced cost, no need to build these towers, just put the antennas there and operate them. It's quick, there is roads ready, there is electricity ready, there is, I think most cases, there is this fiber ready. So just put the cell there and it's working. And often these are in high places, and it means better coverage in remote areas. That is always bonus. And then for us ordinary people, what are the benefits? Of course, it's better coverage and connectivity in remote and rural areas. Like if you are doing hiking, fishing, or something else in the wilderness, it's good also for these reindeer herders, because they are now building these windmill towers to the reindeer herding areas, and those could provide this coverage too. And of course, this emergency services 112 calls can be made in larger areas if you have connectivity. Then where you can put these antennas, what we studied also earlier. One place is this below these blades or wings of the wind turbine. Then you don't have this disturbance. Yeah. So in this area, so then you don't have interference from these blades, and still it's rather high. If you look at these towers, it's 30 meters or maybe even more from the ground. So it's usual cellular base station on top of hill. You have that kind of situation there. So quite good position there. But the problem is how to attach these antennas. I think they do not want to put holes in these structures. They should use something else. Then higher in the tower, so it's this area. The situation is similar. You go higher, you have a bit better coverage, but then you have these blades between you. Possibly these blades are between you and the antenna or base station, or you can go to the top. So it's usually over 100 meters. I think highest are 200 meters, so potentially very good coverage. But then there are these blades are causing you problems, and also this nacelle, this big structure here, size of the bus. is there, and it can also limit your coverage, especially on those directions where that is. And then this nacelle is turning when the wind changes, and that means that you have to have beam handovers, but they are already in the standards, or you have to have rotating antenna if you do not want these moving cells. But that might cause interference. You have to do also this frequency control with the neighboring cells. Challenges, what we have seen, and we don't have answers to all of these. Maybe there could even be further project on these, like this maintenance of windmills or base stations. When you go there, what you have to do? So you have to have first this, if it's very high there, you have to have these climbing and access permissions. And who gives you? Is it the operator of the windmill or operator of the cellular tower? How they agree that? Then do they have to shut down the cellular base station when they do maintenance of windmill? There is microwave radiation and high power. Probably you have to shut it down. So it means no 24/7 operation. That might be critical for some applications. But they have to shut down even regular base stations. So maybe that is not the problem. But the question is how often this is done. How often you have to shut it down. Then this business thinking, it needs more studies, especially if you make it commercial. Of course, it's only for local use of windmill operators. Then it's quite easy. They just calculate should we invest for this or not. But if it's for commercial use, then there is need for calculation. Then who is operator? Is it cellular operator, windmill operator, or some local operator? And then there are always these questions of frequency licenses, and roaming is big problem. Then if you are small operator in the area. Then what we aim to study is this propagation through blades and nacelle. Is one problem. We have not yet found solutions from the literature for that. And then antenna impact on windmill operation. So if we put this 1 meter high antennas on top of nacelle, does it affect to the operation of the windmill? So for the propagation, we have discussed with the windmill operator and think how we can do these measurements easily. We don't have climbing permissions to the tower, so we have to do it from ground. So one possibility is in this picture. So we will have flying drone with the receiver, where we can measure different things of the signal, and then we have vehicle where we have transmitter. Of course, we have to take care of this geometry so that there is plate between the radios. And it's easy to measure the attenuation. It's constant every now and then. It happens there. If you go closer to nacelle, they are more frequent because it rotates more. Speed is different at the ends of the blades than in the center of the nacelle. But that is then impacting if there's big attenuation due to blades, then the impact is higher if you are in the center of nacelle than at the edge of the blades, because there are more these disturbance. We have to analyze also this effect later on. So this measuring of this blade effects is basically what we can do very easily with our existing equipment. But then the more tricky thing is then that if we put the antenna on top of this nacelle and how we can measure it. Basically, you need 100-meter RF cable, and the losses are too high for us. It's not possible, but maybe if the windmill operator persons can put the antenna there for testing the antenna impact on the windmill operation. That is the purpose that we will not rent, but give all antennas to them so that they can install them and put them there. But still we have problems. They have to put the cable inside the nacelle, then they have to learn how to use transmitting radio systems. Probably it must be some kind of signal generator and put it there, put it on. Then we can do the propagation measurements around the area and see how it works. And then they have to go there and shut it down, bring it back, and so. So there are a lot of things to solve before we can do it. And also where we direct this antenna. Probably we are not targeting these 3 or 4-dimensional antenna system, only looking to one direction. And we want to, because if you propagate away from the blades, there's nothing new. We know already how the signal propagates. We want to direct the antenna so that blades are between you and the antenna, the transmitter, so that we can see the impact of blades and nacelle to this propagation. And we plan to do this in the summer or most probably in late August, early September. I think we have to still plan the measurements later on. And we have to also ask the frequency permission and flying permission, but these flying permissions are okay. So we only need these frequency permissions. So. And then final slide is where we are planning to do this is in close to Piteå. There are a lot of windmills, as you can see in this figure. And I think this is only small part of this Piteå windmill area. Okay, thank you. Sweden, yes. Thank you. Any questions?
Harri, thank you. So yeah, open for questions.
Yes, I have one question about this. So, means you are talking about the installation of the antenna in the wind tower. So instead of this, like this is the plate, so we can put behind of this the plate, so the blades will not interrupt the antenna. Like if it is the tower, then blade is this side, so we can put like this here, the back side.
Yeah. But that we know how the signal propagates if there is no blade, because you just use the regular propagation models to predict how it goes. Yeah.
Yes, and another is like when we talk about this wind farm, then we have lot of winds up. So we can use this distributed antenna based system. Instead of putting one heavy, we can put small, so it will not weight it to one windmill. Like in the Piteå, we have lot of windmills.
Yeah.
So we can use this distributed base station phenomena.
Yeah, basically, yeah, but then it's more installations and.
Yeah, but it's increase and it will not burden to one windmill.
Yeah, but even if you put the small antenna, you have to go up, put the radio. Or nowadays, I think there is this AESA. Not RIS, but this AESA, this where you have RF parts and antennas together. You just put them up, and it's optical cable down to your base station. But still, you have to install.
Okay. Yeah.
For every site, you have to install this anyway.
Yeah.
Is it? I think it's big or small base station. You have to do the same same installation.
Yeah, installation is a problem, but yeah.
No, it is one of the features of these parks is that you have many towers relatively close to each other.
Yeah.
So you could it would be an interesting idea to somehow say, can we exploit that? You don't have that anywhere else, right? That you have several high towers in a vicinity.
Yeah.
But yeah, there is the installation the installation
Yeah,
cost. That's true.
But the other thing is that the plates are all in the same direction. So if you're directing antennas to the other direction, you'll miss one direction.
Right.
Yeah.
Right. Yeah. I guess there's a lot of good technical questions to research questions to be addressed here. I have one more question on the business case though. So if you have, I mean, the market has not, let's say, found this solution, right? I'm not aware of many operators that have base stations in these towers.
Yeah.
So what is the main reason, do you think, that the market has not already somehow found this? Why is it not already happening?
I don't know. Basically, you don't need not so many base stations in remote areas. You need some. So
Yeah.
I guess that in one windmill park, you need only one for the coverage of the whole park,
Right.
and a lot of surrounding area.
Yeah, volumes.
Yeah.
There won't be a big volume market for this, right?
If the operators are not now willing to invest their own base stations, own towers into remote areas, maybe they don't want to use this windmill tower.
Yes. Now you mentioned also on your slides, there's quite some work to do probably on the business case side,
Yeah.
on the acceptance of this.
And we have not even seen this feasibility of this thing, so that if this plate problem is too severe, then it does not make much sense. Yeah. At least put them in the top.
Yeah. Good. Thank you, Harri, for this. So let's move on in the agenda. So we have our next speaker is about flexible network infrastructure for remote teleoperation, and that's Aamir Mahmood. He is from Mid Sweden University, and he is online. So yes, we have you here, Aamir. So floor is yours.
Yeah, thank you. I will try to share my screen. So I hope you can see it in full screen mode.
Yes, we see it.
Okay, perfect. Okay, morning, everyone. My name is Aamir Mahmood, and I'm Associate Professor at Mid Sweden University. In this talk, I will be talking about this remote teleoperation use case. Teleoperation, I mean here the ability to operate some heavy machines from a remote location. And when we talk about the remote areas, because if we want to do the teleoperation, it's a demanding connectivity use case for 5G and 6G, and then there is a lack of infrastructure on the remote areas on the northern side of Sweden, Finland, and all these areas, Nordic countries. So then I will be sharing our experiences based on the two Vinnova-funded projects that we had together with some industrial partners. So what are the connectivity needs, and then what kind of infrastructure we need to support this kind of use case, especially in the, you can guess from the picture, is more about the timber handling, because these northern areas, it's the timber heavy industry. So it's related to both the management of the forest supply chain. So here, quickly about the agenda, I will quickly talk about the different use cases of teleoperation and then focus on the forest industry vertical. Then I will give some the needs and challenges that we faced while tackling this forest supply chain management. The project name was to remote timber. And then the continuation of that was going more towards building a robust wireless infrastructure for that use case based on what we learned from the first project. And then I will just give some opinion about where we see the future of teleoperation and what we learned from these projects and what we have for 6G going forward with this use case. So teleoperation, as I mentioned, the ability to control the machines from a remote location. So the areas are diverse. It's more about port automation. It could be used in construction, automation, mining industry, and as I mentioned about the forest industry. So the needs could be different. It could be about handling the dynamic loads at port automation. In the construction automation, it could be the dangerous situations where we don't want the operators to operate at that location. It could be any other hazardous conditions. And then it could be related to basically, if we go for mining and automation, it could be the ore extraction or it's the transportation. And then the forest industry, it covers a wide area. So if I stole this slide because SCA was the project partner. And when we're talking about, okay, why even this Starlink, for example, why they don't have the connectivity in the northern areas. So probably it's what we see that probably we need to advocate the needs, connectivity needs in these areas. So here it shows on the left side the forest that is owned by SCA. It's from if I take the pointer. So here I'm putting this Sundsvall as a reference because they have own the forest in the northern part of Sweden. And on the right side, it's the different operations that are happening because SCA owns the forest and then they maintain. It's not only about cutting the wood, but also maintaining those ones, preparation of the soil and planting new trees. So all these activities are happening in the northern areas. So in this case, if we where the wood is felling, I mean, they are cutting the wood and then it's transported to some terminal, some intermediate points where the wood is stored. So even where the wood is cut, like usually they have one harvesting machine, one forwarding machine that is loading the raw wood to the trucks, and then it's transported to some intermediate location. They call it timber terminal. So that's where it is stored. So here they have many, around 200 sites where these actions are happening continuously. So far, they are saying like, okay, it's operated manually, but in future, it's just they are reporting, okay, what is the logging operation that is happening at this moment at this site, and they get the next task. Okay, now they should move to this site. So in that case, they are talking about, okay, they need the coverage needs, but in future they want to automate that operation. So the machines, the ability to operate the machines from a remote location, because the manning of these sites is always difficult and challenging. So here, in this, the first project that we had, the remote timber, we were focusing mainly on the wood is coming from the forest, transported. But when it comes to this timber terminal, they have 15 sites in this northern part. But in general, in Sweden, there are almost more than 100 sites where there are timber terminals where the wood is coming and stored, and before it's forwarded to the industry or the factories. So in this case, the objective was when the wood is coming here, this heavy wheel loaders that are like 40-ton wheel loaders, the task was to operate these wheel loaders from a remote location. So it's the automation of this workflow for loading and unloading, and we did this use case. If we have one operator sitting at a remote location, it has the ability to operate 4 timber terminals. So it covers this manning needs of these terminals. Mostly they are in a remote location, so manning of these timber terminals is a bit challenging. But what we face is mostly these are in the remote locations, and if we talk about the teleoperation use case, it's a challenging use case in terms of connectivity needs. So it has, because to operate this machine, you need to have multiple views. This machine, it's not only the driving this machine, rather it has to do the intricate operations, the handling of the wood, loading and unloading and storing that wood to the right place. So it's an uplink heavy use case in terms of the video transmission that this machine has to send to the remote location to the operator so that he can operate this machine. So in that case, first of all, lack of connectivity infrastructure, and then fulfilling this demanding connectivity needs of this use case is challenging. So this is how a typical timber terminal looks like. It spans over around 3 to 4 kilometers, and the wood layout is not fixed. It keeps dynamically changing depending on how the wood is coming and how it is moving out of this timber terminal. So this site is close to Sundsvall. It's called Torspada. So we did some drive tests. The nearest base station here was about 3.5 kilometers, and we were looking at what is the throughput that we could get at this location at different places, and then what is the latency. So here, what we observed, based on the basic test, the data rate we could achieve here was 1 to 10 megabits per second at max. As compared to that, if we look at the round trip time using simple ping commands, so it was reasonable within the range. I will express what were those connectivity needs coming from Volvo to operate these machines in a safe manner. So the ping was around 60 to 80 milliseconds, but 60 to 80 milliseconds. So that was fine, but ping is a very simple way to test the round trip time, because it's not testing how the network will behave under different load conditions. So it's not generating the realistic traffic in that case. So in that case, we went towards selecting a certain section within this timber terminal, installing a dedicated base station on that one, and just to provide the coverage in this area. So this was our test area where this vehicle heavy loader was operating. And then the operator was at the same location, but the traffic was routed through Stockholm to this is going to the core is in the Stockholm, so traffic was routed to Stockholm and then coming back to this operator. Operator was located at this, so it was maintaining two sectors, one towards the vehicle, one towards the operator. And this is how if we look at, this is where the vehicle is operating, and the timber height could reach up to 10 to 15 meters in that case. And for the operator, this was the analysis that was done. Okay, now to have the operator to operate in this kind of environment, how many views he needs to operate this machine in a comfortable manner. So there were 11 cameras installed on the vehicle. But there was a proprietary tool that is stitching all these streams together, transmitting, and then received by the operator. So in this case, the requirements that was set was to support all these views. There was a requirement on 50 megabits per second in uplink direction, with the latency of 200 milliseconds to operate this machine safely. So whenever the latency threshold was exceeded, so in that case, the watchdog timer on the vehicle triggers, and it goes into the safety. It just shuts it down, so it's remains static. So in that case, the operator has to go to the machine, and then it has to reset. So during these tests, the tests were conducted over a week. So every day, 2-3 times, it was happening that the machine was shutting down because it didn't meet the connectivity needs. So here it's one quick video. I hope you can see just the wheel loader without operator on itself. So this is how it was handling the wood operations. So in this case, the drivers, they needed certain training before because they lack certain haptic feedback that was not provided. Because a lot of things they judge based on how the vehicle is behaving when they lift the load, or no sound, nothing. So in that case, they needed some training, but they wish they could have the vibrations that they feel when they are really operating that machine. But after certain training, they were able to handle these operations. The other one was about this, the difficult task was this depth estimation when you are loading or unloading. So these certain boundaries, it's hard to guess. It's more, it's difficult, the depth estimation. So that was the good side. Okay, now we have the successful demo, but then if we look at the ugly side, so if I look at some results, in addition to that, I mean, they were operating the machine, we were conducting some measurements. So in that case, what we see was, okay, if we look at these bounds of 200 millisecond, if it is a line of sight condition, I showed you that the area in which the vehicle was operating. So if it, as long as that vehicle is in the line of sight area, it satisfies the connectivity needs. But as soon as you go out of that connectivity zone, you start violating those requirements quite quickly. So just imagine then we want to provide the connectivity needs in the whole timber terminal. So then what kind of infrastructure we need? And the same was for the throughput requirements. In the non-line of sight conditions, it was not satisfying this the requirement of 50 megabits per second. So if we look at how the network was configured, it was a lot of over-provisioning of the radio resources. 1800 megahertz band was allocated 1900 megahertz band, as well as 3.5 gigahertz with TDD, with certain uplink downlink distribution of resources. So in that case, with this over-provisioning of resources, how feasible is that from the one who owns this, from the operator perspective, or the one that is the end user is the SCA, for example, in this case. So what are their, how to allocate these resources in an efficient way? That's still challenging. And then as we move out of this coverage zone, the performance degrades quickly. Then if we look at the timber terminal, it's more a stationary the timber terminal, I mean, the terminal is stationary, but if we look at the wood layout, it's always dynamic. So in that case, it needs more flexible network infrastructure that could handle this connectivity needs. And then we are just operating one machine, and it's uplink heavy use case. So how to satisfy those connectivity needs? So based on this, what we learned, then we move forward to the next project phase, where we envision that, okay, we need more. We need to play more with the RAN architecture, how the RAN architecture is defined to provide coverage in this specific timber terminal. And then also the network slicing. I mean, these new features are coming from 5G, 6G, but they were not exploited. How to handle the let's say the video traffic, the control traffic, because the control is running in parallel with the video feedback that is going to the operator. And then how the videos itself, they are handled on the vehicle side. So operator is given all that information, all this raw information is transferred to the operator, and he is acting based on that. And what if we use more intelligent methods on the MEC level to reduce the uplink demand, basically? And then the other direction that we envisioned was more drone-mounted 5G base station to extend the coverage to provide the connectivity needs on the timber terminal, and then other KPIs that we set. Then to provide this different coverage options, that's where we took. There were two options: either we have a local core and a flying base station on a drone, and then it provides the connectivity, I mean, fulfills these coverage holes in that timber terminal. And the other option was that was coming from SCA. At some places, they do this drone, lift up the drone just to, so that the tower comes in visible range, so that at least we have that typical UE. It's more like a UE, and it has the coverage to the connectivity to the base station. And then it could provide either this access could be 5G or it could be even Wi-Fi in that case. But the one that we demonstrated was in Västerås. So In that case, we had the local core. It was not 5G core, it was 4G core that is provided by Ericsson, that is tested in a lot of different situations. So that's why they didn't went towards 5G setup, but it was a local core, and then we had the drone mounted base station. So in that case, I will show the demo later, but the forwarding machine that was used to test this the connectivity. But in parallel, we did some additional tests. Instead of ping, we use this TWAMP. It's more like a two-way active measurement protocol that allows you to generate different kind of traffic patterns as well, different payloads, and so that is more appropriate as compared to just using pings to measure the network performance. So in that case, we were testing this and this drone base station. The local core was connected to Starlink, and then we had the server, the receiver side was in the AWS server. So in that case, what we observed, surprisingly, the Starlink was providing quite good enough latency. It was like, if we look at the minimum is around 55 millisecond, and the maximum latency that we could see is around 160 milliseconds. So that was satisfying the connectivity needs. And the same, if we look at this forwarding machine, this machine was operated from remote Uppsala. I forgot the distance between Västerås and Uppsala, but it's 80-90 kilometers or something. So then we had the drone flying above with the base station. This was around 30-40 meters, and it was providing the coverage. The coverage was around 3 to 4 kilometers. And then we are this project is still continuing.
Can you start to wrap up? Or?
Yes. So this project is continuing, and then we are looking at the MSC, the role of MSC to reduce the uplink information transfer. We are looking at the super resolution algorithms to reduce the data rates, to compress the videos. This is what we see for the future, as I think Nurul already mentioned about this multi-model data fusion, where instead of giving this raw information, we rather need to go more abstraction of the details provided to the operator to operate in this machine. But the challenging is, it's not only about the driving itself, but then we need to learn about build this environment model, driving model, as well as the task model. That's the actual loading and unloading of operations. So this is the last slide that I have, the future of teleoperation. So, is it something that we need to handle something differently in 6E? But we need more holistic approach. But as Nurul also highlighted, we need to bring in the context of the application, and of course the AI/ML to co-design of communication and control for this kind of use case. These are the project partners, and this project also got the Seal of Excellence from Royal Swedish Academy of Engineering Sciences. It was selected as top 100 project with more impact on the more impact on the society, and is more ready for the commercialization phase. Thank you.
Good. Thank you, Aamir. So that was very interesting. I think we learned a lot about this vertical. I was thinking, okay, I will allow one very short question if there is. We have little time, so keep it short.
I'm not sure it's short, but try. So what we observed when we did measurements with the Starlink, that there are connection breaks up to 10 seconds or sometimes even longer. Have you done driving tests to see how these breaks impact to the driving experience?
They were experiencing some jitterness. Probably we couldn't isolate, okay, those are because of those brakes or something. Is it because of the handover mechanism, or why there are brakes? I didn't know that.
Probably it's related to handovers, at least these long ones. So the next satellite, it's coming a bit late or something, but you do the measurements, and maybe it would be, if you are really doing this, how the driving experience, maybe it would be good to include these break counts, break durations counts also to these analysis or measurements.
Okay, thanks.
Good. Excellent. Thank you, Aamir, once again. Then it's time to move to our last speaker. So we are going to listen to even more insights in coverage, IoT coverage in remote area. And the speaker is Jean Sant'Ana from University of Oulu. Please go ahead.
Oh, okay, there's a. Perfect. Okay, thank you everybody for hosting this event. My name is Jean Sant'Ana, postdoc from University of Oulu, and I've been giving some first insights in the analysis of coverage of HAPS for IoT in remote areas. Of course, that's like the topic of this webinar. So I think if you're here since the beginning of this webinar, you've seen these next two slides. So this is the structure of the Ensure 6G project. This talk is related to this first part, so connectivity in rural areas. And then first question that became like to motivate the use of HAPS of the study on these kind of technologies, like why not to use just to use third-party solutions, for example, Starlink, which is the one that everybody talks about recently. So you've probably seen this picture that Nurul showed. This is a quite old picture, actually, like we took from the beginning of our project, I believe. And then before coming here, I was like, okay, let me check it because you never know, like they are launching satellites all the time. And then, well, if you check it, it's quite similar. And I think, like in the beginning of the webinar, we were discussing a little bit about like why is it like that. So one reason it's most likely like business, as we discussed. So not that many people in these areas. And also it comes with the like how the constellation was chosen to be. So you can see like this part where there's almost no satellites. Of course, there are a few satellites that pass here. And these satellites that pass through this area, you can see that they have some kind of vertical/diagonal orbit. And that's why they end up passing through this region. But most of the satellites that are in the southern part, let's say, they have this tendency to be more horizontal or diagonal, but towards the center of the globe. So they keep rotating towards the center. So you can think about like, what if a country like Finland and Sweden wants to have some coverage, like can they trust completely on a third-party solution on a company that maybe it's not that interest in the commercial, maybe it's only interest in the commercial view of it and not, for example, in serving areas where nobody has connectivity or something like that. So it's always a question to make. So just quick overview, like very simple about HAPS. In this work, we used very simple parameters. We didn't do a very intensive study on the functionality of them. But basically, so they, like with them, we can have some certain control of the area. So on the right side, you can see two types of HAPS. The first one, it's the Zephyr. Now it's from this Auto HAPS, but I believe it was from Airbus before. It was project more than 20 years already. And well, there are some other projects, and nowadays the projects going on, they have this kind of HAPS with the flexible wing, which is the one that you see on the top part. And then, okay, yeah. And then there are these kind of these other types that you can see down. That is the balloon type. This was discontinued by Is it by Google and then was bought by X company? But nowadays it's just discontinued. And then like the ones that came after this are these kind of balloons that are like the Zeppelin style of HAPS. But anyways, so the altitudes of them goes from 8 to 50 kilometers. There's altitudes like they kind of depends on the kind of group studying them or the alliances studying them, but we can say it's not as low as a UAV, not as high as a LEO satellite. Another pro of this, because of this altitude, that there is possibility to indoor or communication without line of sight. First, of course, it depends on technology parameters, but we can see that there are some room for that. Well, because it's not a mature technology, not that many companies still going there. They are, for now, like limited by the battery weight. So most of them are powered by solar energy. But like there's a limited time where they can keep working there without landing. So we have to wait for battery technology to improve so they can improve the flying time. And because of not being mature technology, it's still hard to say they are a long-term solution. So that's why we are doing research on it. Then just very few brief of the technologies we choose to study here. So the reasons, like we wanted to first do some check of HAPS for IoT. The reason to doing LoRa and LR-FHSS is because we had some previous studies on that. We wanted to like analyze something quick. We had previous work on this was easy for us. So LoRa and LR-FHSS are both physical layer technologies from LoRa. LoRa is a bit older, was the first they released the chip spreading spectrum modulation. It has 7 spreading factors that basically you exchange the transmission rate to reach longer distance. So with SF7, you transmit faster, but you don't reach that further. The opposite with the 12. And then LoRa, compared to LR-FHSS, has lower power consumption and it can benefit from multiple gateways. There are many studies showing that. So very good for ground networks. And then there's LR-FHSS. It has a frequency hopping spreading spectrum. It's divided into like its transmission packets. It's divided into header and the payload. The thing with this technology is that it has some replication inside the headers. So headers are transmitted 3 times over different very narrow channels. And the payloads, they are coded with convolution code with 1/3 or 2/3 rate. And then this whole coded payload is split into 50 bits fragments and then transmitted over several channels. They are 488 channels, hertz channels. And then for successful transmission, you need 1 header and 1/3 or 2/3 of all these fragments. So you have some redundancy from the header and from the fragments. All of this makes this technology makes it a very high interference mitigation. And also it has a very longer communication distance. We'll see this in the results a bit further. So this makes LR-FHSS very interesting for non-terrestrial communication satellites and HAPS. This was one of the reasons it was designed, and it's being studied and used a lot for these kind of scenarios nowadays.
Do you know the hopping rate?
It's so the header takes 233 milliseconds, and then the payload is 102 milliseconds each.
One hop per second or something.
No, actually more, because then for each header it transmits the header and then you hop to another. And then transmits another header hop. So for each 233 or 102, it keeps hopping. And then the number of there's some structure of these hoppings to follow the regulations. So there are many. I think overall you can think about 35 channels to hop. But before this 35, you also choose 1 out of 8 grids to hop. So there's a lot of, that's why it's very good to mitigate interference. So this is the system model we adopt. So very simple. We have free space path loss with rich and fading and log normal shadowing. And the parameters of this model, they are function of the elevation angle. So we can kind of see the elevation angle being like important on this case, of course. Then the coverage area, we set up like a circle where the maximum radius is given by the minimum elevation angle that we consider for coverage. And then also, so we have this model, and then we also have like transmissions might incur into collisions, and if there's a collision, there's also an voltage. So first, for the connectivity results, you probably see some similar pictures in Nurul's presentation before. So the first result, we just set the HAPS at 30 kilometers height, and then we just change the distance of the devices and check the connectivity probability. You can see the distance and the elevation angle axis, like they are basically the same, the equivalent. And then, of course, you can see that the higher SF, we have like a bit higher outage because the distances are a bit like not as long as the higher spreading factors. And you can see the LR-FHSS is the same as the SF12. So we can see that like there's still some good margin, especially for the SF12 and for the LR-FHSS to work with this kind of setting of parameters. But then another interesting result we have is that maybe we are interested in the worst part of the network, which is at the border. So how is the coverage there? So we just set similar results, but then with the minimal angle. So for that, we just kept increasing the HAPS height to get this result. So as you increase the height with fixed angle, you have the radius of the network. So we put the device on the radius of this network. So you can see that of course, for a smaller elevation, for a smaller height, we have like better coverage, but then this incurs into a smaller footprint, so a smaller coverage area. So here you can see a bit of the trade-off of the HAPS height and the elevation and the area coverage. And then finally, it's not like a very novel result, but this is showing the collision probability of the LoRa and LR-FHSS. So this result is like not novel for this work. There are some previous works showing that. But then here we can see that the collision probability for the same number of devices from LR-FHSS, it's way smaller than for the LoRa spread effect for LoRa. Thus showing what we said before, that the scalability of LR-FHSS is way stronger than LoRa. So just some conclusions and further work. So this was a very basic and first insights of HAPS for IoT. We showed that LR-FHSS proves to be a better option than LoRa for the HAPS communication as well as the satellite, and that the HAPS might be a potential future solution for this type of IoT communication. And for future work, we are planning to do some kind of technical economic analysis of HAPS, LEO satellites, and UAV remote IoT and compare them, investigate these aspects like the reliability and scalability as we've done here, but also costs, energy consumption, the architectures of the HAPS system, and also the regulatory challenges that we might face. And that's it. Thank you.
Good, thank you, Jean. One short question, if there is any.
Do we have this frequency hopping system? We have LoRa, but do we have this frequency hopping so that you can do real measurement-based comparison?
So this has been like quite new compared to the other LoRa. Across Europe, there are many people like already like doing works with that, and there's like real setups, especially for satellite communications and LEO communication. I don't know if we have at the University of Oulu now, but like we can definitely buy the devices and check it.
Yeah, because if it's interesting, it would be worthwhile to have it in test network.
Yes, for sure.
Yeah.
Good. Thanks again, Jean. That brings us to the end of this webinar. So I want to thank again, first of all the speakers for their interesting insights. I think we have learned a lot, got new insights about and perhaps some more about the challenges, about the verticals in remote areas. And even more, I want to thank the audience, all you in the audience, for attending this and for listening and showing interest in the work of these two projects. So with that, I close this webinar and say thank you to you all. Bye-bye.
Thank you. Bye-bye.